Hello there, welcome to our webinar. My name is Kelsey Reed and I'm on the technical sales team here in Canada. Today we're coming at you from our Calgary facility where we manufacture most of our products here in-house. Today we're going to be talking about Michell Instruments. They provide moisture, water and hydrocarbon dew points. Today the focus is going to be shifted to the hydrocarbon dew point analyzers. Before we get going, if you guys have any questions, there's a little chat box at the bottom of your screen. So go ahead and put your questions or comments in there and one of our team members will be able to help you out. Before I pass it over, I just want to talk about nVent really quick and what we can provide for you. We have our M series, which are M60, M70, and M90, our oxygen, water, and CO2 analyzers. Most people know us for our H2S analyzers, which is our 330S and our 331S. That's a Div 1 and a Div 2 option. We have our portable analyzers for H2S. Those are the sulfur sentry analyzers. We have our gas chromatographs, also coming in Div 1 and Div 2 options. That's our 131 and our 132. Our tunable filter spectrometers, or TFS, again coming in Div 1 and Div 2 options. As I mentioned, we're going to be talking about Michell today. We are a rep for them, and yeah, you can see that on your screen as we provide Michell instrument analyzers. We also provide sample conditioning systems for most of our analyzers, and we also provide buildings, enclosures, and probe assemblies. We do our best to be a one-stop shop. You come in here with a problem, and we'll provide you a full solution for that. I'm going to pass over to Nigel. He's with Michell, and he'll be able to walk you through it today.
Hello to everybody. This is a webinar on hydrocarbon dew point measurement theory. It's being presented by Michell Instruments US and nVent Engineering. My name is Nigel and I'm the technical director for Michell, and pleased to give this presentation to you. So let's begin with the definition of hydrocarbon dew point. There are, as with many things, shades of grey and shades of reality with definitions, but the theoretical definition, according to the ISO standard, is the hydrocarbon dew point is the temperature at a given pressure at which the hydrocarbon components of any hydrocarbon-rich gas mixture, such as natural gas, will start to condense out of the gaseous phase. So what does that actually mean? This can be defined or can be expressed in terms of an operational definition for the temperature at which the first visible film of a hydrocarbon condensate is observed. So the hydrocarbon dew point is therefore not a speciation. It is not looking to determine whether that hydrocarbon that drops out is a C4, a C16, a C12. It is the first condensable. So with a hydrocarbon dew point analyzer, you will not get a speciation or a definition of that first dropout, but you will get the temperature at which it occurs. Now, as we go on in this presentation, you'll find that hopefully you'll learn that there are lots of variations in that through different measurement techniques. And what is the first condensable and the temperature that occurs is very, well, not dependent, but can be influenced by the measurement technology and the methods in which the measurement is formed. So let's move on to a recap of the theory regarding hydrocarbon dew point. Hydrocarbon dew point has what is known as a retrograde curve. It's a phase envelope that folds back on itself. So in this image you can see that the hydrocarbon dew point line is the purple cerise line, and it rises sharply, has a plateau, vertical plateau for about 200 psi, and then as it rises it folds back on itself. Now we also have within natural gas a water dew point, and you can see that that is a more conventional curve. Okay, it's not linear, but the important aspect for measurement of hydrocarbon dew point in natural gas is the relationship between the hydrocarbon dew point measurement and the water dew point measurement. So if we are all out here on the right hand side at say temperatures of 75 F at 400 psi, then we're going to be in an all gaseous phase. As we cool that gas, we're going to hit the hydrocarbon dew point line first. If we're up here at say 1100 psi and we're at a temperature of say minus 60 F, then we're going to be in a liquid phase. And it's understanding how these relationships work, in particular into this area and this area, where we can end up with two-phase liquid, two phases of fluid within a pipeline. So if we start out here at 400 psi and we cool the gas, we're going to go through the hydrocarbon dew point line and cut it and dissect it, and in here we're going to have a gas liquid phase, so a two-phase, but the liquid is going to be a hydrocarbon liquid, whereas up here at the higher pressures we're going to cut through the water dew point line first, and we're going to have a water phase, liquid water phase as the second phase. So it's important to understand the measurement pressure and the temperature at which you're measuring to ensure that you're measuring a gaseous in a gaseous phase and making a valid measurement. Now the situations or the tariffs vary across the world. For example, in Europe they measure at this point here, which is called the cricondotherm. So the cricondotherm typically has a plateau, a vertical plateau of around 200 psi gauge from about 350 to 450. You can see it changes very little, and this is the reason that the Europeans measure out here is that this is the worst case scenario. So at 400, 500 psi, this is when you're going to start getting a phase change in your fluid in your pipe. Whereas in Canada, the typical measurement pressure is at line pressure, which can be 1100, 1200 psi, and is typically in this area here. So with different sampling systems and different analyzers, we can remove the water dew point to ensure that the hydrocarbon dew point is the first dew point that is measured. So please, bear in mind this phase envelope diagram and refer to this phase envelope as you consider the measurements that you're making. Now, a phase envelope diagram like this can be dropped out of GCs, it can be dropped out of or constructed through hydrocarbon dew point analyzers and water dew point analyzers. So it's a piece of information that is readily available and but important that you have and you get to know and understand. Okay, so knowing or having a recap of the theory, then why do we measure? What's the importance of the measurement? The measurement, well, as with any process, the measurement importance is all about the continuous operation of the process. Now, whether that process is providing a flow of gas, or whether it's a quality measurement, it really doesn't matter. The measurement is to ensure that we operate for as long as possible within conditions that are determined to be either safe or within a contract or within a specification. Excuse me. So typically there are three categories of users, and the users have different definitions of the measurement or the importance of measurement. The processors, they're looking to maximize their revenue. So what do we mean by that? They're looking to operate for as long as possible within a tariff with reduced downtime in order to pass as much gas through their system as possible to achieve the maximum revenue. The pipeline operators have a slightly different focus. Yes, volume through pipeline is extremely important, but also the safety of the pipeline, the repair costs associated with pipeline, the integrity of the pipeline is important. And with the various positioning of compressor stations, also we're looking to avoid the damage of compressor stations due to two-phase fluids passing through the pipe. We don't want liquids to hit a compressor and cause any damage. End users, they often have two aspects to their requirement to measure. One is they want to know the quality of the product that they're buying, and the second one is that they want to know that they can keep what measures they need to take to keep their power station running. As you can see from the images, there's images of damaged turbine blades from a power station, and that's caused by liquid hydrocarbons repeatedly hitting the turbine blades and causing fractures and wear, and in this case total destruction. And then the right hand image is an ice water dew point hydrate, but it will be a combination of hydrocarbons and waters, and you can see the potential that will have if that gets down to a compressor station. So, knowing that it's important to measure, how do we measure? There are many different ways to make the measurement of hydrocarbon dew point, and there are different technologies. There have been technologies around since the late 70s, early 80s, and there are several key providers in this field. But in essence, there are four measurement technologies, shall we say. The most common one and the oldest one is the dew scope, or what is now called the Chandler scope. That uses a manual sampling method, and it chills the mirror down while the operator is looking through a lens over the mirror, and the operator determines the temperature at which he identifies the hydrocarbon dew point. This is a very operator intensive measurement, trained operators that are using these on a regular basis can recognize the dew points and the difference in the dew points that they see. but it takes time to understand and takes time to practice the technique. It is a truly manual technique. The second method, which is shown here by a GC, there are many GC providers out there. What is shown there is a typical Daniels GC. These give equations of state calculations. Now there are various equations of state that give you a calculated hydrocarbon dew point, and they have their place, but they have limitations. It's often a nice way to perform a measurement because the GC is there for other purposes. The GC is there for the analysis of the gas, it's there for the Wobbe index and the heat value, and so to be able to tack on a hydrocarbon dew point measurement within the same unit because of a firmware calculation is often seen to be a nice way to go. But as we'll discuss later, it has some disadvantages. Then we go to a relatively new measurement technology, SEERS. It uses spectroscopy. It's say new to it's 5 to 7 years old to the industry. It has some attractive benefits, but it also again requires knowledge for operation. And then the final measurement technique is an automatic optical condensation analyzer. So if we go back to the first one, the dew scope, it's a automated version of the dew scope. Instead of using an operator to identify the formation of the condensate, it uses an optical path, and instead of using a bottled gas to cool the mirror, it has a thermoelectric heat pump, a Peltier. So it takes the operator out of the equation and performs a measurement on a cyclical basis that is highly repeatable. So let's go back to the dew scope. This was the primary measurement technique as we outlined, and as we said, it's operator dependent. And what does that actually mean? Well, this slide shows you the 10 different rings or different images you can see for different forms of condensate forming. And so this is why an operator can't, or an individual can't just walk up to a dew scope and perform a measurement with confidence. The operator needs to have used a dew scope for a good period of time, make many different measurements in many different environments, and be able to recognize the difference between a alcohol dew point and a water dew point, or a glycol contamination to an advanced condensation ring. So don't get me wrong, there are plenty of trained operators out there that can do this day in, day out, but the measurement is not straightforward, and it is only taken or at the point of time when the operator is performing the measurement. So yeah, there's lots of areas where this can be useful as a snapshot in time, but it does require a trained operator to perform the measurement. The GC, as outlined, it's a equation of state calculation, and this chart here is showing the difference between a C6 plus and a C16 analysis using the same equation of state on the same gas. So with a C6 plus GC, the calculated hydrocarbon dew point at cryo-condensatherm pressure would be minus 66.5 degrees F hydrocarbon dew point. But if you were to have a effectively captured sample and it was performed, analysis was performed down to C16, then that same equation of state would report a hydrocarbon dew point of positive 49 degrees F dew point. So that's nearly 100 degrees F swing because of a calculation deviation based on the knowledge of the heavy components within a natural gas. So yeah, we're looking at some serious deviations, and if this is a custody transfer measurement, there's a lot to be learnt from this. In more recent times, over the last 10 years or so, then C9 plus analyzers have become more common, and that does quite significantly narrow the deviation. But it's not a, it can still be seen not to be a truly representative measurement. It is a calculation based on an equation of state through speciation, and if the speciation isn't complete, then as you can see, the heavies have a tremendous impact on the hydrocarbon dew point calculation. So yeah, some points, some notes of comment just to support the statements I've just made. The important one there is the final bulletin, is that an analysis procedure for C1 through C14 is described in GPA 2286-95. So what they consider to be an accurate calculation through an equation of state would be for a C14 analysis. The heavies down at the bottom end make that significantly difference to make that C14 measurement an important speciation to achieve. Now, as I mentioned, that can be done in a remote lab through sample, but then please bear in mind that the issues with sample grab, sample consistency, the integrity of the sample through transportation and through the analysis from the BOM into the GC also plays into part. There is nothing like a direct measurement to improve the integrity of measurement. Taking a sample always risks the introduction of contamination. So SARES is a new technology. It uses a crystal based on top of a Peltier, and it uses two different wavelengths to determine a hydrocarbon dew point and a water dew point at the same time on the same gas. It's based on spectroscopy, so it does have some significant advantages, but it's still, even after 7 years or so, it's still being field proven. There are some erroneous measurements and conditions that are difficult to measure with an end user, say a gas-fired power station or a custody meter transfer station. But these days, with the inclusion or the development of fracking and shale gas and the dramatically changing gas qualities that can be seen even at the end user level, let alone in pipeline transmission, it's still finding its feet. So we come to the automated optical condensation analyzer. So this is this was the second measurement technology that was developed from the Dew scope, and as said earlier in the presentation, this is an automated version of the manual method. So it's got a lot of history to it. The first, there are two or three companies that perform this method of measurement. It's got a lot of installs through many different applications in many different string compositions throughout the world. You know, we can go from Asia, China, through the US, through to Europe and Russia, Eastern Europe, through to Russia, and all the way back round to China with locations of installs. However, the key players that provide this measurement technology do have some fundamental measurement differences in the technologies. So with dew point in water, the fundamental measurement technique known as chilled mirror has been around for many years. For water dew point in ultra high purity gases, the chilled mirror measurement technique is the standard measurement technique throughout the world. So whether you go to NIST in the US, or whether you go to PTB in Germany or MPL in London, to measure water vapor in UHP gas or compressed air, to measure it accurately, a chilled mirror will be used. So what we have, the essence of the chilled mirror is that the mirror is a polished surface. It's not a conventional glass looking mirror, it's a polished reflective surface that has a thermometer or a PRT to either be embedded in it, as shown in this image, or it can sit between the Peltier heat pump and the mirror. With the Peltier heat pump, you can control the temperature of the mirror. Excuse me. You can control the temperature of the mirror through electronics and through control circuitry, so you can drop the temperature of that mirror. So if we have a sample gas coming across and we drop the temperature of the mirror, that the condensate is going to drop out of the gas in the form of dew if it's above 32 degrees F, 0 degrees C, or it's going to drop out as ice if it's below the 0C 32F. Otherwise it's known as a frost point in the metrology world. There is an area called supercooled water, but because water doesn't change state immediately at 32 degrees F to ice, but that's another topic for another conversation, another webinar. So once the ice or the water forms, then the light source gets scattered. The light source that shines onto that reflective mirror gets scattered, and the change is seen by the detector. Now, if you remember the image in the previous slide, there was we show a spill of gasoline, petrol, on the tarmac. The key difference between a chilled mirror measurement with water and with a hydrocarbon is that water has a tension, hydrocarbon doesn't. Hydrocarbon scatters, as can be seen by the image on the previous slide, and it disperses very quickly over a wide area, and that can make the detection of the hydrocarbon much more difficult. So Michell developed a measurement called the dark spot measurement technique. And this uses the basics, the essence of the chilled mirror for water dew point, but the mirror is fundamentally different. Instead of having a flat, highly polished mirror, we have a concave mirror. We have a mirror with a depression in it, and that mirror is actually acid etched, so it's a rough surface. So we're achieving the opposite of the water dew point chill mirror. So when it's dry, we have a deflected or diffused signal, as can be shown in the image on the left hand side. And as the hydrocarbon condensate forms on the mirror, it forms and adheres to the acid etched concave mirror, and it forms a dark spot. So it gives a iridescent ring to the around the detector, and as can seen by the artist image, there's a dark spot formed in the center of the detector. So we're going from a diffused measurement to no measurement using this hydrocarbon dark spot measurement technique. So if we look at a series of measurements at different temperatures, we can see that at the positive 10 degrees F dew point, hydrocarbon dew point, we have the diffused measurement. That would indicate a dry mirror, and as we decrease the temperature of the mirror, we get that ring forming until the 20 degrees F measurement there on the bottom right hand image, where we can see the mirror now is being flooded with hydrocarbons, because we've got that image of an iceberg or a flood area of liquid hydrocarbon condensate forming in that mirror. So we can see the progression of the formation of the condensate as the mirror temperature drops. So in terms of a measurement that would be seen, dry sensor, some condensate beginning to form, more condensate forming with the first spot at the bottom of the mirror. This is where we would consider the dew point to be to a excessive condensate or a flooded mirror forming out and going well beyond the dew point measurement. So with this measurement technique, it is a cyclical measurement technique. As the dew forms, we can look at the bring the cursor onto the screen. Here we go. So we can, if we start with a dry mirror, this element would be a dry mirror, and as we start to cool the mirror, we get down, and then we heat the mirror back up. We drive the mirror temperature back up to drive the condensate off the mirror. So we always start with a clean mirror, and again you can see it's repeated, it drops down and drives it off. Now if we look, the purple cerise line is the detection signal. So on a dry mirror, we've got this diffused value which is nothing. But as the mirror temperature drops, we get an increase in a millivolt change. So we're getting a detection rise in the lack of signal from the diffused mirror. So it's like a inverse measurement. Our signal goes up as we get less measurement. And after lots and lots of development and comparisons with trained operators, in the majority of cases there's a millivolt value of 275 millivolts, which ties very nicely to the Chandler scope dew point measurement. So once the detection signal hits 275 millivolts, we consider that to be the hydrocarbon dew point, and then the heating cycle takes place, and we drive the condensate off the mirror, and we go back to the diffused no signal measurement with the detection signal. So you can see here roughly we're looking at 10-minute intervals, but this is 10 minutes, so 6 measurements an hour, but this is unattended, this is repeated, so it's 6 measurements an hour, 24 hours a day, 365 days a year. And this is what the sample cell looks like as a assembled item. You can see the sample cell is relatively small. We're looking at a base plate here of roughly 4 inches square, and the height of it is probably 2.5 inches. Stainless steel throughout, so 3-1 material certs, NACE is not a problem. We've got gas in, gas out, and we've got a pressure sensor to determine the measurement of pressure, and then we've got the emitter and the detector as shown in the artist's image earlier on. And the Peltier is this is the mirror surface with you can just make out the concave mirror, acid etched mirror, and the PRT is embedded in the mirror, and this is the 3-stage Peltier that controls the temperature of the mirror. So this square black block underneath the Peltier is the heat sink for the Peltier. So if we're cooling this mirror, we've got to dump the heat from the Peltier out into this block, and this block sits inside or sits on the inside face of an analyzer to act as a big heat sink, and this gives us quite a sizable depression. So we can have roughly from an ambient temperature of 60 C, we can get a depression down to about -5 degrees C, so we've got a 65 degrees C at ambient temperatures. But once we get the performance of the Peltier does deteriorate as temperatures cool down. So at -10 we can achieve a -63, so we've got a 50 degree depression capability. So the analyzer does require it does have a heater in it to maintain a 20 degrees C temperature within the analyzer to increase the depression capability of the analyzer. So this is what an analyzer would look like from Michell. It's called the Condumax 2 actually. There was a Condumax 1. The Condumax 1 used the same measurement principle with the concave mirror, acid etched mirror, and the Condumax 2 came along in early 2000s, 2003, 2004, because of the development of and the effective costs of Peltier heat pumps. Before that, the Condumax 1 used a vortex tube with compressed air to control the cooling rate of the mirror. Now the Condumax 2 is able to do that under a lot more control in a lot smaller package, and give repeatable measurements that aren't dependent on any other facilities. So it comes with the typical approvals. It's IEC, EX, ATEX, CCSA, US approvals. We also have the TRTC, and we can achieve in Metro and kosher on on request. The other nice thing about the Condumax 2 is that it is operational through a thick glass screen. So the monitor there has a twist face to it that unscrews, but the 4 buttons there, up, down arrows, enter and select, can be operated using the thumb of an operator through a comprehensive menu system to set the analyzer, to configure the analyzer in the working environment. So no hot work permits are required to set the analyzer up once it's up and running. To commission the analyzer does have to be open to provide a purge of the analyzer before it becomes operational. So there's some examples of field measurements. There's an operator there performing a manual dew scope method. You can see the bottle of gas there, and him cooling the mirror down, and to the left of that is an automated system. It's shown with a bottle of propane. This is lab grade propane. What's happening here is that the Condumax is being validated. Lab grade propane has a very well defined and well known hydrocarbon dew point, and so by verifying the Condumax against the lab grade propane, there's great confidence in the measurement performance of the analyzer. So the analyzer does require some warranty. It's not like all analyzers. It performs as well as it's looked after. You can see there that there's some sampling system in front of the analyzer. You go back to the phase envelope and the retrograde curve. We don't want liquids entering the Condumax. The Condumax can perform a water dew point measurement and a hydrocarbon dew point measurement on the same gas stream within the same enclosure. And we would advocate that the hydrocarbon dew point cell is replaced on a bi-yearly basis, every 2 years, whereas the water dew point sensor is replaced on an annual basis. And these can be done with service exchange sensors and service exchange units. What does that mean? It means that 2 units turn up at site, and the technician can install those units, and within 3 hours a unit can be back up and running. The calibration data is held within the sensors that are supplied, and so there's very little work to be done in terms of matching the sensors to the units and to the analyzer. We would advocate that a propane test is performed for the hydrocarbon dew point to give the site confidence, but beyond that it's a straightforward procedure. So what are the applications? The applications for the Condumax are points of sale, and points of sales can vary between gas companies to end users, and also gas processing facilities. So throughout Europe, the Condumax has been sold widely since since its introduction in early 80s in version 1, and through definitely predominantly in 2000s through the version 2 for gas custody transfer, through with Europe being a much smaller entity, or broken up into entities, than Canada or the US. Every time there's a border change, there's two Condumaxes, one either side of the fence, to make a measurement for the hydrocarbon dew point. Hydrocarbon dew point is a required measurement, is part of the gas custody transfer legislation in Europe, and as it has such an effect on the Wobbe index and the heat value of the gas being sold. So yeah, it becomes a very important measurement in Europe, and also within China. Here in the US, we don't have that legislation, but the interest and the value of the measurement is becoming much more important with the rapid development of shale gases. Shale gases through gas processing facilities are enabling rich gases to be blended with lean gases to reduce the operating costs of gas production. So lean gases can be sold according to contract specifications, and instead of being flared. But it also, where there's an abundance of rich gas, it enables liquids to be removed out of the gas, and still while that gas still makes a contract requirement. So a gas company can double dip with a rich gas by selling the liquids, the hydrocarbon liquids, as well as the gas. So this would be a typical hydrocarbon dew point reduction plant, where they're separating out the NGLs. There's two sides to the plant. There's the water reduction and there's the hydrocarbon reduction. This is an image that is well known, I'm sure, to all the people that are sitting in on this webinar. Yeah, you can see that the importance of the hydrocarbon dew point measurement to determine the maximum NGLs and condensates to be removed possible, while still being in compliance with the sale of natural gas for distribution to domestic households and industrial users. Power stations are becoming a bigger application, again with the development, or with the increase in shale gases and the number of fields where shale gases play and tar sands fields play. The variation in hydrocarbon dew point can be very significant from one location to another, 200 yards apart. They can be significantly different, and with gas-fired power stations, they have what's called a superheat capability, to provide the gas additional heat to ensure it's wholly gaseous before it passes into the burn chamber and then onto the turbine to power the turbine. So if the superheat is not vaporizing all of the liquids, or if there are any liquids in the burn chamber and it's not being burnt efficiently, then the resultant wear can be seen on the turbine in the image on the right hand side. Power stations, they earn their money by operating. So if they have to pull a turbine out, they're losing money. Typically, a turbine interval for a pull, it should be somewhere between 7 years, maybe 10 years. In some situations where rich gas has been supplied, I have heard of turbines being pulled after 18 months because of damage being done and vibration being seen from the turbines. So the measurement of hydrocarbon dew point to determine the confidence of the superheat, which is typically 55 degrees, applied to the gas, and whether that is applying enough heat to ensure that a wholly gaseous mixture is being burnt and presented to the turbine. It's an important measurement. So back to pipelines and purchases of gas. Often comes down to contract rules, and whether you're a power station, whether you're a pipeline, whether it's a domestic distribution, it comes down to the contract that for the purchase. Is the hydrocarbon dew point specified within the contract? To have a 1020 BTU gas with a high hydrocarbon dew point is very different to having a 1020 BTU gas which is lean, and it gives you a very different gas composition. Knowing who's responsible for the compliance for the gas conditions is important, and then having the ability to measure the hydrocarbon dew point to determine whether you're in compliance, and the statement of compliance can be made, and also to see if there's any benefits in being able to reduce the richness of the hydrocarbon dew point that is going into a domestic environment. Gas is an important source of fuel, and you don't want to sell rich gas at lean prices if at all possible. So the other element of hydrocarbon dew point, and we've mentioned it, I've mentioned it a couple of times, is the starting with that phase envelope, is the water dew point. The Condumax has a aluminium oxide based sensor for its water dew point, but Michell does also do a TDL, tunable diode laser analyzer for moisture, and this shows a combined hydrocarbon dew point and TDL unit from a single sample stream. So the Condumax is the analyzer on the right hand side, and the TDL is the analyzer on the left hand side of the enclosure, and you can see the sample cell, single pass sample cell mounted at the very edge of the enclosure. Now with nVent, Michell has been partnered with nVent for 3 to 4 years now, and we've got a very good partnership. We've been selling Condumaxes and TDLs through nVent into various markets throughout the Canada, the US, and beginning to go further afield into the world. And between us we can offer other measurements as well, such as oxygen, H2S, total sulfurs, and also a GC for measurements within natural gas. So that concludes the webinar for this subject. I hope it's been of interest. We'll be pleased to answer any questions, and do appreciate your time. Thank you very much indeed.
Thanks so much, Nigel. I hope that helps you guys understand Hydrocarbon Dew Point a little bit better. Stay tuned for upcoming sessions, and please complete the survey that should be popping up onto your screen now, and tell us what you guys want to hear about next. If you guys have any questions, we'll hang around for a little bit longer, but also you can feel free to contact us and we'll be happy to help you guys moving forward.